This lesson is going to discuss the algorithm used to convert from decimal to binary, and you could use the same algorithm for conversion to other bases, decimal to octal, decimal to hex. In our case, we're going to use decimal to binary, and once we get it into binary, we'll use the same algorithms to convert from binary to octal or hex that we already use in the past. So let's take this example. If we had the decimal number 13 and we want to convert that into binary, this process here on the left, the algorithm, is that we take the decimal number, here we have 13, and we look for the largest single binary digit that will fit the number, um, fit below the number given. So if I write out my binary digits, let's write those out. These are my binary places. So this first place is the ones place. The second place is the twos place. Then we have the fours place, the eights place, and the 16s place. That's enough for this particular number since 13 fits below 16 and above 8. So I'm going to take 13 and say, does 13 fit below 16? No. So I would put a 0 there. Does 8 fit below 13? The answer is yes, so I'm going to put a 1 there, which means that I'm now using one of these groups of 8. So I would take 13 minus 8, leaving me with a remainder of 5. Now I continue the process looking for 5. Does 4 fit below 5? If the answer is yes, I put a 1 there. I take 4 from 5, and I'm left with 1. Continue the process. Does Does 2 fit below 1? No. 0. Does 1 fit below 1? Yes. And so now I can get rid of, and so I would do to complete the process 1 minus 1, 0. I have a remainder of 0. I'm finished. So the decimal equivalent of 13 in binary is 1101. Okay, let's try that again. Let's pick a number like decimal 25. December 25. There we go. Decimal number 25. See what that is in binary. So I'm going to write out those binary digits again. Get several of them. So these are the ones, the twos, the fours, the eights, the 16s, the 32s. So I come along. Does 32, so I'm working on this one right now. Does 32 fit below 25? No, that's a 0. So I move now from here to here. Does 16 fit below 25? The answer is yes. So I put a 1 there and I do the subtraction. 25 minus 16, which is going to be 9. Now I go to the next column. I'm done with this one and I'm looking at the next column. Does 8 fit below 9? The answer is yes. So 9 minus 8 is 1. And so I know that it's not going to be a 4 because now once I get to a 1, I know the last thing I'm going to use is that last column. I can shortcut the process at that point, knowing that all the rest of these will be zeros, and the final one will be a 1. So I have decimal 25 is equivalent to 11001. Okay, so looking back at our algorithm, this algorithm works. It's easily followed to end up with the correct answer. The nice thing about this algorithm, as presented here, is it is something that you can teach a computer to do. So you can actually implement this algorithm in code to take a decimal number and convert it into a binary equivalent. In our case, one of the things you can do with this is you can implement this as in an Excel spreadsheet using Excel's capabilities to repeat calculations over and over again. So hopping over, we can see a Excel spreadsheet set up to do this exact same kind of thing. Here we have the power. This row X is the power um, of 2. The row 2 to the x is the placeholder. So you can see we have the 1s placed, the 2s, the 4s, the 8s, all the way on up, in this case, up to a 16-bit value of 65,536. We place the decimal number that we wish to convert, and what will happen is this row, the row remaining, will scan down looking for the appropriate place that fits below that number. So here we have 13 and 16. 13 does not fit below, or sorry, 16 does not fit below 13. Next, 8 does fit below 13, so the spreadsheet places a 1 here. And then the remainder now is here in the next digit. The remainder is 5 after we've used 8. So 13 minus 8 is 5. So does 4 fit below 5? Yes. So 5 minus 4 has remainder 1. So this is implementing that exact same algorithm. So the pattern is the remainder checks to see if the 2 to the x power fits below this remaining, and if it does, it initiates this as a 1. If not, it puts it as a 0, and then it does this number minus this number to get this remainder. And you'll notice that I can just multiply this number times this number and subtract it from this number to get the amount that's left here. Because whenever there's a 0, that's going to be in this case, 13 minus 0. So I'll continue to have 13 until the algorithm finds a spot. So you'll see that 13 is equivalent to 1101, which is the same as we got when we did our example. This automatically updates, so if I were to change that to another number, like 72, you'll notice that it automatically calculated over again. 72 gets carried through until it finds a number that's less, 64, and that's where the first 1 appears, and then it carries the remainder through until it finds a spot. And so we have 72 is equivalent to 10001,000. Then this algorithm also converts it into octal and hex. That's what this lookup table is for hex. And so the decimal value 72 is the binary 1001000. It's the octal number 110, and it is the hexadecimal number 48.